Hi, I'm Colin. I'm a software engineer at Eventual. Images come from everywhere. User uploads, web scraping, satellite imagery. You might have a 4K image from a professional camera or a tiny profile picture from an iPhone, but your downstream systems need them standardized. Your ML model expects 256 by 256, and your web interface probably needs some consistent thumbnails. The solution seems simple. Download the images, resize them to your target dimensions, and then just save the results. So let's write some Python code to do exactly that. Here's a straightforward Python approach that most engineers start with. We write a function to download and resize a single image, and then execute this function in a loop over our image URLs. Today, we'll be working with a dataset of around 300,000 images, but we'll just start with our first 100. Looks like it's working. We're reading 300,000 rows and then processing images sequentially. But this is painfully slow, and this is probably going to take you a couple hours. Let's look at the CPU utilization. Only one core is active and is barely getting utilized. Your code is completely single-threaded and so much time is spent waiting for network I/O. But even if you added custom multi-threading to speed this up, you'll hit a different wall. Processing images is memory intensive. Memory usage climbs steadily as processed images accumulate. Within minutes, you're going to hit slot space and eventually crash. Your script can't handle real-world usage. We need something better. This problem is fundamental to how image processing works. Here's what happens when you process a single image. Start with a 500 KB JPEG file. When you decode it for processing, that becomes anywhere from 3 to 12 megabytes of uncompressed pixel data depending on the image dimensions. That's a 6 to 24 times memory inflation just from decoding. So what are engineers going to do today? Manual batching. Instead of processing all images at once, they have to break the work into smaller chunks and then distribute those chunks across multiple machines. They spin up their own clusters, distribute batches across nodes, and then hope they guess the right amount of batching to run their job. If you run batches of too small or too large, you're not going to get the best CPU utilization. Daft takes a different approach. Instead of manual batching, Daft uses streaming execution with dynamic batch sizes. Let's see this in action on a single machine. We're going to run the same script as before, processing the first 100 images. Daft processes images in batches at a time. It downloads a few images, processes, resizes them, then frees that memory before moving to the next batch. The result? 100 images processed in 4 seconds. Stable memory usage and high CPU efficiency. No manual tuning required. But you see, Daft doesn't just shine on a single machine. The same code that gave us the streaming execution locally can scale seamlessly to a distributed cluster. All I need to do is point Daft to running on my array cluster. And this is as easy as setting daft.context.setRunArray. Now we're going to run on the full workload, 300,000 images. The way this works is that it distributes all the files across each of the machines in the cluster and runs our streaming execution as we would do locally on each of the nodes. Now, let's see how long this is going to take to process 300,000 images. And it's done. 37 seconds to process 300,000 images. Daft's streaming approach works for all multimodal data, such as documents, videos, audio, and anything with memory inflation characteristics. The same code will scale from your local laptop to a production cluster, processing millions of images, scaling from 16 to 100 nodes, or maybe 10 million images. It's a single line of change. Ready to stop fighting with memory explosions? Pip install Daft today. Thanks for watching.